Okay, just a reminder that we've looked at end behavior and we're looking at what happens from the left end and from the right end or at the left and right end. And so as x goes to negative infinity, what happens to f of x or y? In this case, it's going to positive infinity. As x goes to positive infinity, in this case, f of x is going to negative infinity. When we validate that, you'll see that we're asked to support our conjecture numerically. So we're going to be using a table of values. And you can make that decision as to what your table of values is going to look like, but I'm just telling you that that's what you need to do. And so the first thing I want you to do is graph this function. Um, to be able to look at the end behavior, what you think it's going to be, and then we will support that numerically. Now, in this case, when you graph that, you should be able to tell what's going to happen. So I'll just give you a minute, type it in your calculator, and I'll come and see what it looks like. I think my window maybe went from -5 to 5, something like that. Oh, just kidding. My graph really went from like -10 to 10 and -10 to 10. So graph it, maybe let me look at a couple of pictures. Yeah. And you should have an idea from looking at your graph of what's happening as things go to positive and negative infinity. I'm seeing a lot of graphs that look like this graph. And so our expectation is that as x goes to negative infinity, and sometimes when I'm recording like this, I'll write in yellow. As x goes to negative infinity, it appears as though f of x is going to go to negative infinity as well. As x goes to positive infinity, it appears as though f of x is going to go to positive infinity. We don't want to get super attached to a graphing calculator because as you go on in your education, sometimes then that is taken away from you or you're not allowed to use it. So we also want to validate that with a table of values. The easiest kind of table to make is a table that has, large values to the positive and negative side. So the table of values that I have starts at -10,000, -1,000, -100. I'd like everybody to make that table, or well, you don't have to make it like that, but I'd like you to put in x equals -10,000, and I want you to look at that table of values because I want to see what your answer looks like on the table when you do that. So -10,000. And so looking at this one, if it that whole list on this particular calculator is -1e12. Did you get something like that? -1e12. If you scroll over to it, just do that a second and then look down. It's kind of giving it about the same. Sometimes if that's not quite that high of a number, like 12, it might actually show you the value just to kind of let you know that that's what it is. So I'm just gonna look at that. And so -1e12, if you remember what that means, -1 is like -1.0, the decimals right there. This is really -1 times 10 to the 12th. That's how your calculator writes that. So -1 point, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to move that 12 decimal places that way. So that is a very small number or very negative number. And so -1 times 10 to the 12th is a very negative number. So take a minute and look at what it is for -1,000. And is that negative 1 times 10 to the, tell me the power, to the ninth. So negative 1 times 10 to the ninth, negative 100, negative 1 times 10 to the sixth. And I I figured my table was incorrect on here. That's why I'm not showing it right away. But I think I can fix that now. So that should just be a 12. And then the 9 and the 6 are good. At 0, it's 4. In this instance, we don't really care about that. It's not like we're looking like we were before. And then 1 times 10 to the 6th, 1 times 10 to the ninth, and 1 times 10 to the 12th. Just a note to self, I do expect your answers to be given in scientific notation and not using that calculator like shorthand, just so that you're aware as we go through that. So now we want to use this limit notation. So our answer is the limit of f of x as x goes to, and it's n behavior, to negative infinity is equal to negative infinity. And that means as x goes to negative infinity, this graph is also going to negative infinity. And then the limit of f of x as x goes to positive infinity. So as we go out to positive infinity, that is equal to positive infinity. And often that'll be the case, not always, but often. And so when you're asked for end behavior, and I'll just tell you really, I don't think that's too hard of a concept, but what people forget is what it's actually asking when it says, what is the end behavior? Because on your test or a quiz, it might just say, describe the end behavior. Well, this is what I want to see, that limit as x goes to negative infinity, what is that? And as x goes to positive infinity. So the next problem we'll look at is this one. My graph on the picture is not good, but it's not terrible, but it's a little misleading. So take a minute and graph this on your graphing calculator. Make sure when you do that, it's x plus 2 in parentheses over parentheses x squared minus x minus 2. So take a minute and do that problem as you're looking at that. And I don't know what a good window is. What did you use as a window? Negative 10 to 10? Yep. A window of negative 10 to 10 looks like a pretty decent window. It might be a little hard to exactly see what's happening as x goes to negative infinity. And you might notice that as you look at this graph, and here's the book author graph, and it's not great. The book author graph looks like it goes below this x-axis, but I believe it does not. And we'll support that with our table as we go. So again, we'll just kind of plan this through. As x goes to negative infinity, what does it visually look like is happening to y? It's actually getting closer and closer to what? To 0. And so that looks like it's getting closer and closer to 0. As x goes to positive infinity, maybe it's going to 0, maybe it's going to a half or a third. You know, at least on the book author's graph, it looks like it could do anything. Does it look like on your calculator it's going to 0? So probably that's going to 0 as well. So things don't always go to infinity. Sometimes they go to 0. And actually, look at this graph. Think about our previous questions. Is this continuous? For the whole for all real numbers, no. It looks like it's discontinuous several places. So we do have to be careful, because do you agree that f of x does go to negative infinity at some point? But The question here is to describe the end behavior. And so even though this goes to negative infinity, and here it goes also to negative infinity, there it goes to positive infinity, and there it goes to positive infinity, that's actually fairly close to that y-axis. So end behavior is what is really happening when we go way out that way and what is really happening when we go way out that way. So those are things to kind of consider as you're looking at these problems. It's not asking, does it ever go to positive or negative infinity? It's actually asking, um, does it does it what happens as x goes to negative infinity and as y goes to negative infinity. Same thing, we're getting a little better at the table of values, hopefully, and I have to tell you that it is super important that you are capable of making these tables of value. And sometimes when people don't always write everything down or aren't physically experiencing that, then later on it doesn't work out that great as you're looking at that. And it's always a little mystery to me as to whether the book authors have this right. But if you put in negative 10,000, are you getting negative 1 times 10 to the negative fourth? Okay, and I'm seeing enough validation that I agree with that. When a few of you were gone, we said that on the calculator, and I'll just go back to that real quick. On the calculator, it'll do like negative 1 E12, and just a reminder that I will expect to see negative 1 times 10 to the 12th as we do that. And so then for this one, what is the end behavior? Well, the limit as x goes to negative infinity of f of x, as x goes to negative infinity, is 0. The limit, because hopefully we agree that I didn't really write what this one is. Negative 1 times 10 to the negative fourth. Remember our decimals here, so when we go 1, 2, 3, 4 places, that's 0.0001, and so that's very close to 0 in this case because it's a negative exponent. So the limit of f of x as x goes to negative infinity is 0, and then on the other side, as x goes to positive infinity, the limit of f of x as x goes to positive infinity is also 0. And it should make sense to you that that could also go to a value instead of 0 as it's getting close. You know, an easy way to think about that is if we just translate everything up 3 or something, you know, and just had a big plus 3 there. Then instead of going to zeros, it would go to that 3 mark or something like that. The next thing we want to look at is what if we have more than 2 variables? If we have more than 2 variables, when we're looking at it here, we want to hold one variable constant. And when we hold one variable constant, it's going to have no effect on our answer. And I want you to think about that a minute. See this 2? When you're thinking about putting in these really far away from 0 negative or positive numbers, really, does it matter that you're taking 10,000 and adding 2? No, it really doesn't. And and then you're squaring 10,000 and subtracting 10,000 and then subtracting 2. As that gets even bigger and bigger, is it going to make a difference that you've added 2 there and subtracted 2 there? No. A constant is not going to have any bearing. Even if that had been 2 million, it doesn't matter, because think about when this is much, much larger than that, then adding 2 million isn't going to be making much of a difference at all. So that's what I want you to kind of think about in this next problem. Do you agree that there are 3 variables here? E, X, and Y. So the symmetric energy function is E equals x squared plus y squared over 2. If the y value is held constant, what happens to the value of symmetric energy when the x value approaches negative infinity? So We're allowed in this case, if we're holding y to be constant, we can pick a value for y to be. And even if all of us pick different values, eventually, as x approaches negative infinity, the same similar thing is going to happen in either case. So y is constant. And then what happens as x approaches negative infinity? And our equation is e equals x squared plus y squared over 2. And again, you know, I can make y 1, I can make y 1 million, and long term it's truly just not going to matter. So I can just set y equal to 1 or a value of your choice. Might as well make it just pretty easy for myself. Then e is equal to x squared plus 1 over 2. And what's going to happen to that x squared plus 1 over 2 as x goes to infinity? What is going to happen? Can you figure that out without looking at a graph and really without making a table? If this is a big number and I square it and I add 1 and divide by 2, is it going to positive infinity? Is it going to negative infinity? Is it going to some value? What do you think? Positive infinity. And if this is super negative, I'm squaring it, and so then it'll become positive. And so when I take a big negative, a negative that's big, and square it and add 1 and divide by 2, it's going to be the same as a big number squared added to 1 and divided by 2. Even though I'm dividing by 2, as it gets super big, things are still going to be getting bigger and bigger. So this one, the limit of E, I'll call it that. I just will ask that, you know, we're careful. I don't really like that it's E as x goes to negative infinity is positive infinity. They don't call it E of x or E of anything because they got the two variables there. Um, but that's what's going to happen for that one as it goes on. I want to just look at this next one that's a multiple choice problem, and I want to ask you to think about, and actually this is I, not 1. So the illumination E of a light bulb is given by E equals I, which is the intensity, divided by D squared, which is the distance in meters from the light bulb. If the intensity of a 100-watt light bulb measured in candelas is 130, what happens to the value of E as D approaches infinity? So think about this. It, just looking at this, and we'll have I as a constant. It's 130. So this is E equals 130 over D squared. Now think about D getting super big. Super big, and we're squaring it, but then we're taking 130 divided by a super big number. What's that getting close to? It's getting close to um, 0 as we look at that. Because as if think of it as, you know, 130 over 1,300,000 or something, you know, because it would cancel kind of easily. So it'll be getting closer and closer, 1 over a super big number, and so that'll be getting closer to 0 as we go through that. So just some things to think about there. I do want to move on to extrema and rates of change. And so this is 1, 4, extrema and average rates of change. they're about the same. Close, yeah. Okay, the next thing we're going to look at is intervals, where graphs are increasing, decreasing, and constant. And that will help us find extrema. And extrema are maximum and minimum values. And they might be absolute extreme values, or they might be just relative at that little area extreme values. And so if we can see that something is increasing and then it starts to decrease kind of in that area, there's maybe an extrema as we look at that. Our intervals are always going to have parentheses. So does that mean they're including the endpoints or not including? They're not including the endpoints. So when we give an interval, it's saying, you know, from here to here, we're not really counting that endpoint um, as we look at that interval. And so we'll look at graphs that are increasing, decreasing, constant, maximum, minimum, extrema, average rates of change, and a secant line. Um, in my opinion, average rate of change should not be hard because it's like finding a slope. We're taking a curve, and so I'll kind of draw. We're taking a curve. We pick 2 points on that curve, and we approximate um, the rate of change from this point to that point by finding the slope of that green line. And so slope we're familiar with, y2 minus y1 over x2 minus x1. And this is called a secant line. A secant line hits the curve in exactly 2 spots, or 2 spots in that area. Um, you'll maybe be told, because you'll have a rule and all that kind of stuff. You'll have an f of x, and it'll say, what's the average rate of change between x equals 1 and x equals 4? So if for instance, you know, where it says x equals 1 and x equals 4, you'll have to find y, f of 4, y2, and y1, f of 1. Oops. But then it's just a matter of subtracting the y values and subtracting the x values to find that. You don't have to write anything from this slide because there's a detailed slide after this, but I just want you to look at this. You should agree that visually this is increasing from negative infinity to -5. By the way, be careful of this. Even in pre-calculus, we had a problem like this recently, and it's always x that you're talking about. These intervals are the x interval. It's not saying how high this goes, you know, as the y value. It's saying walking along that x-axis. Where am I looking and what is happening to my graph? So if I'm walking along the x-axis here, do you agree that I'm looking down, but it's getting higher, 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 higher? I step on it, it's still getting higher, higher, higher. So from negative infinity to -5 on the x-axis, that graph is increasing. And then, so that's that interval. And again, we'll see these rules. And then from -5 to 0, it's constant along there. We don't care what value it is, but just that it's horizontal as we look at that. So from -5 to 0, constant or flat. And then from 5, or excuse me, from 0 to infinity, it appears as though it's going down as we look at that. Okay. So this is our next key concept. So take a few minutes and write yourself a note about this. And so essentially a function f is increasing in an interval I if and only if for any 2 points you would pick, a positive change in x results in a positive change in f of x. So a positive change in x results in a positive change of f of x. So notice this backwards writing again, and you see that a little more and more as we get through things. So the y1 is less than y2 when x is 1 is less than x2. So saying what those y values are, that's an increasing kind of situation. And you might sketch just a little picture of that as you go. So then decreasing happens when there's a positive change in x, but it results in a negative change in f of x. So for this, y2 or y1 is greater than y2 when x1 is less than x2. So it goes in kind of the opposite direction. And then the function is constant. When there's a positive change in x, results in a 0 change of f of x. Doesn't mean f of x is 0. It just means that there is no change. So f of x1 and f of x2 are equal when x1 is less than x2. Okay, so you can use your table of values. And again, in this section, you're supporting your answer numerically. So a table of values is appropriate. And this one says use the graph of the function f of x equals x squared minus 4. So you might just want to sketch that graph. I've already got it there on that one because we've looked at a bunch of these. But will you put that in y equals? And the reason I asked you to do that is we're going to look at a table of values and go by 0.5s. And it says estimate intervals to the nearest half of a unit on which the function is increasing, decreasing, or constant, and support your answer numerically. So for this one, do you agree that it has a minimum at x equals 0, correct? Yes. And that visually, um, as as I'm walking along this x-axis, my y values are very high, and then they're coming down lower, 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 lower. And so from negative infinity to 0, it's decreasing. And then when I look at it from here, instead of it going down, it's starting to come back up. And then from 0 to positive infinity, it's going to be increasing. Do you agree with that? Okay, so we have to support our answer numerically. And, excuse me, so we're going to make a table. It's not going to be a real, we don't have to go far out, but we'll go -2, x values of -2, -1.5, -1, -0.5, 0, 0.5, 1, 1.5, and that's as far as I'm going to go on that one. Oh, did I miss any? No, I don't. Yeah, I just didn't go all the way to 2. And then find f of x values that match that. And I'll need a little help with that table. This table is very easy to make on your calculator, so just type in y1 as x squared minus 4. When you set up that table of values and you're at table set, start the table at -2, but then make the table go by, or delta table, whatever it says right there, make it go by 0.5s, and then you'll just easily get that table as you go through. And Emily, I think you have it, right? Will you just read things to me? And, yeah. Okay. So for this, we're just validating that. At 0 is where it kind of hits that as we're looking. So from negative infinity to 0, it's decreasing, and then from uh, 0 to positive infinity. Oops, that looks like an 8 too much. It's going to be increasing as we go. And so two things you have to do when you're giving these. You have to say if it's increasing, decreasing, or constant, and you have to give the interval for that. So f of x is decreasing in the interval from negative infinity to 0. And again, we said this already, but always with parentheses. And f of x is increasing in the interval from 0 to infinity. So that's what's happening there. I'd like to look at one more problem today, and then we'll kind of be done with this part so that we've gone through this. And this one is a little bit different. And so when you graph it, I'm going to actually ask you to graph it on your calculator, and I want your window to go from -5 to 5 and from -5 to 5. So I have a picture of it here, but I want you to graph that as well. Graph this. And And you'll notice that things are not all happening at grid marks. So we are going to the nearest half again as we look at this. So we'll make a table of values. I'm going to go to, it looks like -2 should be far enough. So x equals -2. And since I only have to go to the nearest half, it really doesn't matter if my minimum is exactly at a half. I'm just gonna use my intervals to the nearest half so I can kind of get an idea of what's happening. So -2, -1.5, -1, -0.5, 0, 0.5, 1, 1.5, and 2 for that one. So take a minute and see what you get for that table of values. Ashton, do you have that table handy? Okay. Let me know when you've got it. At -2, do you have something yet? 6. And then tell me the rest of those. 1.875. Okay. Oh, you know what? Do this. Go second table or second window, and then start the table at -2, and then go down 1, and then go by, arrow down, and then go by 0.5. And then go second table or graph, yeah. And now you should just have them there. Do you? I think this one is a value at -0.5. -0.375. And then, yep. And, oh yeah. What did I miss then? Oh, 1 is 0 again. Okay. So 1 is 0, and then this one is what? 1.875. There we go. Yes, I know. It is very much a pattern. So by our table, when is, first it's decreasing from -infinity to where? To -1/2. It's decreasing. So from here to there, those are decreasing. Then what happens? From -1/2 to where? To 1/2. What's happening? It's increasing. And then what's the next interval? Well, okay, if we stopped at 1/2, then we start at 1/2 to where? Infinity. To positive infinity. And what's happening? It's decreasing. So there's our next interval, decreasing. Say that again. I don't know what you mean. Just say yes.